I'm curious.
Okay, let's start. So today we'll go over one graphing example from start to the end. We'll talk about kind of all aspects of graphing, and then we'll start talking about optimization. So the problem will be as follows. Sketch. Okay, so here's the function x plus x to the power 1 over 5 plus 12 divided by x plus 12. Usually you'll have to find the derivative and second derivative yourself, but if there's no time for this, then well, we'll just give it to you. So in this case, you don't really have much time, so I'll give it to you. We also have not that much time, so probably at least the second derivative will be given to you. I don't remember about the first one. So basically, we have a function. We are given the derivatives. The question is, sketch the graph as precisely as you can, meaning, well, your graph should be increasing where the function is increasing, decreasing where the function is decreasing, concave up, concave down on the same interval as the function. And well, I mean, all the main features of the graph should be the same as those for the function. It should represent the graph of the function itself. Okay, so let's start. The first step would be to discuss where this function is defined. I mean, it would be nice to know where not to try to sketch this function. At what points we don't want the function to be defined in here, so we'll discuss domain. So let me ask this in this way. Where this function is not defined, what value is it x? Negative 12, yes, so x shouldn't be negative 12. Anything else? Well, no, that's it. So we might be a little bit suspicious about So minus 12 comes from the 0 denominator. We might be a little bit suspicious about x to the power 1/5. We know that, say, something like x to the power 1/2 would only be defined for x which is positive. But this is x to the power 1/5, and you raise it to kind of odd power. We take 5th root of x, and we can take odd root of whatever number, positive or negative. And also it's a positive power, so even 0. It makes sense even when x is 0, so that's it. Just x not equal to minus 2. That's the domain. Okay, next let's discuss what can we infer about this function from the derivative. So I want to understand where my function is increasing, decreasing, and so on. For this, I want to understand something about this derivative. Is it positive? Is it negative? Well, as it is written, well, not that obvious. Maybe I can factor it to make it a little bit more obvious. What is it? So try. The problem here is with the denominator, or with the numerator. I can't really say by just looking at it whether it's positive or negative. But I'll write it in this way. I'll write it as 12 over x to the power 4 over 5. And then I bring both things to a common denominator. I'll write the second thing also as something divided by x to the power 4 over 5. What is this something? X, yes. So to get x to the power 1/5, I should subtract 4/5 from 1. And now you can rewrite it in much simpler way. It's just 12 minus 4x divided by x to the power 4 over 5, x plus 12 squared. Now it looks much easier for analyzing it. Now I just see at what points it might change sign. These points are the zeros of this expression, and that expression. So the points where the derivative might change sign are, well, minus 12 obviously, 0, and 3. This 3 is 12 minus 4x is equal to 0 when x is 3. Okay, so let's look at this expression. 12 minus 4x, x to the power 4 over 5, x plus 12 squared. And here I'll have x smaller than this, x between, and x bigger than that. Okay, so 12 minus 4x. This might change sign when x is equal to 3. It's equal to 0 when x is 3. When x is really large, somewhere over there, 12 minus 4x, what is it? Positive or negative? Negative, yes, of course. When x is large, it appears here with minus sign, so the overall expression is negative. But then it becomes positive. X to the power 4 over 5. Might change sign around the point x equal to 0 because x to the power 4 over 5 is 0 when x is 0. But actually it doesn't. If you look at x to the power 4 over 5, it's 5th root of x to the power 4. But x to the power 4 is always positive, regardless of what x is. So it's positive for positive x, and it's also positive for negative x. That's because, once again, this power 4 is given. You multiply x by itself even number of times, so you always get positive answer. And similarly about this, even though at the point minus 12 it is 0, once you take x plus 12 and square it, you always get a positive answer. That's because of this squaring. So for derivative, which is, well, the product of those, will have a positive sign here, a positive sign here as well, still positive sign here, and negative only once you get all the way up to here. Let's also look what happens to the derivative at these breakpoints. So at minus 12, you see that this is 0 and this is denominator. So here derivative doesn't exist. At 0, same story. 0 to the power 4 over 5 is 0 and it's in denominator, so it doesn't exist here as well. At 3, it is 0, and that's it. Sorry? Yes. So about the function. So the function is increasing, then it is increasing, then it is still increasing, and only then it decreases. Well, it sounds a little bit kind of ridiculous to say that function is increasing, then it's increasing, then it's increasing, and then it decreases. But that's what we have to do. We'll see later that it will be just wrong to say that it increases all the way from here to there. We'll see on the graph what happens. Okay, so my function is increasing in these intervals, decreasing there. So what can I say about these breakpoints? At x equal to minus 12, my function, the derivative of the function does not exist. So what can I say about this point? Well, it would be critical, but actually it's not critical. The thing is, my function is not defined at this point. This point is outside of the domain. It's really outside of any considerations about the function. It's not critical for the function, it's not an inflection point for the function, it's nothing. My function is not defined at this point. This is outside of the domain. The next one, x equal to 0, is a little bit better. Yes, it is critical by definition. This point now is in the domain of the function, but the derivative does not exist. It might be of different kinds. It might be a point where the function has vertical tangency, or it might be a corner. And we'll have to decide which one it is. How to distinguish a corner from vertical tangency. A good idea will be, well, what is a corner? A corner is when the derivative from one side is not the same as derivative from the other side. And the vertical tangency is where the derivative is, well, when the tangent line becomes increasingly vertical. Yeah?
I think your first derivative is wrong.
Is it?
You're missing a 5 in the denominator. Because I've been doing it and then I just don't know why you did that.
I mean, the check you're claiming I'll have to actually compute it.
Well, I computed, well, I checked on the Wolfram. And
So you say that I'm missing the 5 here?
yeah.
Well, it won't change basically anything?
Yeah, I won't change, just making sure that.
Okay, so with this small correction,
Sorry.
about the second derivative.
Because the midterm's coming up, I'm a bit nervous, I can't do derivatives, so I try to do it.
Sure.
Yeah.
Okay, sorry. Sorry about mistaking you. Okay, so anyway, so we are back to discussing this point. We want to understand whether it's a corner or a vertical tangency. And to distinguish those, it seems like a good idea to compute what are the tangent lines nearby. Are they different from the two endpoints, or are they the same in both vertical? So let's compute the limit of f prime of x as x goes to 0. So this is f prime of x, it's limit 12 minus 4x over 5x to the power 4 over 5 x plus 12 squared as x approaches 0. So what happens here? The numerator approaches 12. The denominator, well, this part approaches 12 squared. This part is a small and positive number. That's important. That regardless of whether x approaches 0 from the left or from the right, this thing is positive, small and positive. So overall quotient is large and positive. So this limit is plus infinity. So now I'm absolutely certain that x equal to 0 is a point of vertical tangency. The tangent line, as you approach the point 0, becomes increasingly vertical. So that may be the kind of the hardest point of the three. The other one, well, it's obviously critical. The derivative is 0 here. And it's also a local maximum. The function is increasing, then decreasing. Maybe a small comment about this x equal to 3. It's tempting to say that it's a global maximum as well, an absolute maximum as well. But well, you can't say. If the function were continuous, then you would be able to say that, well, yes, my function is increasing all the time, all the way up to this point, and then decreases, so it has no choice but to have an absolute maximum here. But my function is not continuous. It might have some jumps. For instance, here, it might behave like this. Increase, then jump, then increase, 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 and then have only a local maximum. It's possible for this jump to be big enough for this not to be a global maximum. So for now, we'll just stick with this statement that it's a local maximum. Okay, so maybe questions about this part, about what can we tell about the graph from the derivative. Yeah, it's positive derivative. Okay, so here I'm looking at this expression, x goes to 0. This part, the numerator, goes to 12, right? When x is very small, this is close to 12. This part is close to 12 squared. So both these things, both terms are positive and non-zero. Their quotient is 1 over 12. This thing, x to the power 4 over 5. First of all, it is small, that's important. But the other important thing, it is small and positive. Because of this to the 4. X to the power 4 is always positive. So you are dividing a number 1 over 12 by a really small positive number. What you are going to get is a large and positive number. So this 4 is what makes it always positive.
Why is x equals 12 outside of the domain?
X equal to minus 12 is outside of the domain because, well, the function is not defined when x is equal to minus 12. It is a vertical asymptote, yes. So for now we are just I mean, yes, it will be a vertical asymptote, but we will discuss it later. And for now we, once again, can't be completely sure. Because, you know, it could be outside of the domain, but have limit from both sides. So for now we don't play with this vertical asymptote. We'll have to check it separately. Yeah.
Yeah, why is x equals 0 critical, but why does x minus 12 exactly?
Okay, so first question about critical point. Critical point is any point, well, inside the domain where the derivative either doesn't exist or is equal to 0. So here, this point is inside the domain and the derivative does not exist. So it is critical. Second question, why is minus 12 not inside of the domain? Well, you can't plug minus 12 inside of this function. You can't divide by 0. Okay, other questions? Okay, so we'll need some space on the board. So I'll probably just copy some of the results that we found to here and not erase it later. So f increases on the following intervals minus infinity minus 12, minus 12, 0, 0, 3, f decreases on 3 infinity, x is not minus 12, x is equal to 0, vertical tangency, and x equal to 3, local maximum. So I just copied for myself these results, and maybe it's, well, just a copy of what we found. Okay, let's play the same game with the second. Yeah.
Is the tangent line critical point?
Yes, it is a critical point.
So
If the
meaning like-
derivative doesn't
okay.
exist, it's
Yeah.
automatically a critical point.
Okay, yeah.
Okay, so third thing. What can we infer from the second derivative? Of course, we'll talk about whether the function is concave up and concave down at different intervals. For this, we'll have to decide whether this second derivative is positive or negative. And quite conveniently, it's already factored for us. So, second derivative. So, I have these factors: x plus 2, x minus 8, x to the power 9 over 5, x plus 12 cubed. And they might change sign at the following points: minus 2, 8, minus 12, and 0. So minus 12 is the leftmost, minus 2 is the next one, 0, and 8. Okay, so let's look at each one of those. X plus 2. It becomes 0 when x is minus 2. To the right of it, it is positive. To the left, it is negative. Yeah. Say again?
The 8. Negative 12, so negative 2, 0, and 8.
Yes, 8. Here's 8.
Oh, 8. Oh.
Okay, so next term is almost as simple. It becomes 0 when x is 8. It is positive when x is greater than 8. It's negative otherwise. Next term, x to the power 9 over 5. It is 0 when x is 0. Now for this one, let's think for a second. It's the fifth root of x to the power 9. So both exponents are now odd. If you start with, well, if you start with a positive number, you're going to get a positive answer. But if you start with a negative number, you raise it to the power 9. You still get a negative number. Then you take fifth root, still negative. So it's positive for positive values of x, negative for negative values of x. So maybe just a small comment. The difference between this and that, why this one does change sign and this does not change sign, is basically here both things are odd numbers and here one of them is even. If the number is even, it's going to be positive. But if it's both odd, then the sign of x is the same as the sign of the answer. Okay, and similarly for this one. It becomes 0 when x is minus 12. When x is greater, it is positive. Obviously, when x is smaller, x plus 12 is negative. Then you raise it to the power 3, still negative. Okay, finally, f double prime is a product. So here it's a product of 4 negative things. It must be positive. Then it becomes negative. Then it becomes positive once again. Negative and positive. So what does it tell about the function? Well, the function is concave up, then concave down, concave up, concave down, concave up. So it seems that we'll have kind of such kind of thing. Okay, so that's about where the function is concave up, where it's concave down. Let's discuss what happens at these points.
Did you look for asymptotes?
Maybe I'll once again squeeze here.
Always.
What happens to the second derivative at these points? If x is equal to minus 12, second derivative doesn't exist. And that's obvious. When x is minus 12, my function doesn't exist. So of course its derivatives don't exist. At other points, at x equal to minus 2, the second derivative is 0. At x equal to 0, second derivative doesn't exist. At x equal to 8, second derivative is 0. Yeah?
Sorry, I just had a question here. Why is it that if you plug in a negative number to x to the power of 9 over 5, that's still negative?
Okay, so let me try an example. Minus 1 to the power 9 over 5. It's the fifth root of minus 1 to the power 9. What is minus 1 to the power 9? Minus 1, yes. What's the fifth root of negative 1? It's some number whose fifth power is negative 1. It's minus 1. So basically, and the same thing happens for any negative number. You can find a negative number whose, I mean, you first raise it to the power 9, it becomes still negative, then you take its fifth power, it's still negative. So basically, if you take a negative number, raise it to its odd power, or kind of quotient of two odd powers, you're always getting a negative number as a result. But if one of those is positive, then you get positive. Hey, sorry, if one of these things is even, then you're going to get a positive. Okay, so let's talk about these points. Minus 12, minus 2, 0, and 8. This one, once again, it's not an inflection point, it's just outside of the domain. We don't talk about it. At other points, my function is continuous, and, well, definition of inflection point is my function changes concavity around this point. It's not about the second derivative at this point, it's just about change of concavity. And yes, to each one of those points, concavity does change. So the other points, x equal to minus 2, x equal to 0, x equal to 8, are all inflection points. Yeah.
Do you think it's y values with it, or does that sound?
So, I mean, in this particular question, our task is just to sketch an accurate graph. So we'll, I mean, once we try to sketch the graph, we'll see whether we actually need the y values. It might be kind of, well, we'll come to this point, we'll just see. If we need them, we'll compute them. If we don't need them, we'll just
So if it
see why.
asks for inflection points, just x values or both?
I guess the Excel is saying. I mean, of course, the question might ask you to find the x and y coordinates of the following. Then you can provide the y coordinates. But I mean, for now, we'll just use the x coordinates.
So the point is whenever your incoming switches. So can it happen? So your if it's a corner then and it switches in cavities?
Yes, put the radius. Okay, so once again, an inflection point is not just about the second derivative being, say, 0, or not about the second derivative being 0 or not existing. No, it's about my function being continuous at this point and changing concavity. If for some reason I had a function which is concave down and then concave down, but the second derivative was 0 in between, it would not be an inflection point. It's important to understand. But here my function is changing concavity. Okay, so before I forget, I will just copy this to here. F double prime is concave up on minus infinity 12, minus 12, then from minus 2 to 0, then from 8 to infinity, 12 decay down on the rest. Sorry, f decay down. Minus 12, minus 2, and 0 to 8. And the inflection points, x equal to minus 2, 8, 0. Okay, so I got that what I found out from the second derivative. Now let's talk about asymptotes. Yeah.
For the limit is for you were finding vertical and to that point and then you took the limit it went to positive infinity, right? So how do you know if it's a corner?
So if the question was well, somewhere here in the place where that I erased, we tried to make sure that the point was a vertical tangency point. And for this we computed the limit of f prime as x approaches this point. And the question was, what would happen if it turned out to be a corner point? So what would happen is that the limit from the left of f prime of x would not be the same as limit from the right. This would be a corner point. So if one of them is pi, the other one is 12, it's a corner. If one of them is plus infinity, the other one is minus infinity, it's a corner. But if both are plus infinity, it's just a corner. Okay? Yeah. Here, yes? So here, you see what happens when x is small. Regardless of what is the sign of x, this x to the power 4 over 5 is positive. So if it was, say, x to the power 9 over 5, then it would be different from the two sides. But here it is, both sides are positive, and the rest is just one of the
So that's an inflection.
Okay, so that was just a remark. Yeah? Probably just like this. I mean, try something like s to the power 4 near 0.0. It has exactly this feature. Yeah. X equal to 0 is an inflection point. It is. The concavity is changing. So once again, the inflection points are not where the second derivative is 0. They are also not where the second derivative is 0 doesn't exist. I mean, it's an indication that at this point might be an inflection point. But definition of inflection point is where a function is changing concavity and is continuous. Only this is, well, a sure sign that something is an inflection point. The fact that second derivative is 0 doesn't exist, well, it only raises our suspicion that it might be an inflection point. But it doesn't prove it. The only thing which proves it is change of concavity. That's the definition of inflection point.
So then your second derivative is a corner or a
No, second derivative. Yeah.
For that part, limit of f prime of x approaching 0, that's to find the vertical asymptote, right?
Find vertical tangency.
Vertical tangency.
It's f prime. It's the slope of the tangent.
What if we find the slope of the tangent is negative, then it's also an isosceles, right?
It's also vertical tangency, but one of them looks like this, the other one looks like this.
Okay. Yeah. Thank you.
My function is the question was why this point is point of vertical tangency and not an asymptote. My function is continuous at this point. There is no problem with plotting in 0 or nearby values. If 0 is just well over. Okay. So let's now discuss vertical asymptotes in G. So at what point my function might have a vertical asymptote?
X equal negative 12.
X equal to negative 12. So now this is not about the point, it's about the line. X equal to minus 12 might be the vertical asymptote. But it's not sure that it's a vertical asymptote. You have to actually check. My function is not a quotient of two polynomials. I have this x to the power 1 over 5, fifth root of something. So I'll have to actually check what happens from both sides. I'll have to check what happens to my function as x goes to 0 to minus 12 from negative side and from the positive side. Okay, let's compute this limit. What happens to my function as x approaches minus 12 from the negative side? Well, let's look. The denominator approaches 0. The numerator, well, approaches something. Let's compute what it approaches. As x approaches minus 12, x plus x to the power 1 over 5 plus 12 approaches minus 12 plus minus 12 raised to the power 1 over 5 plus 12. So it's minus 12 raised to the power 1 over 5. So the numerator approaches some negative number. So two things are important about this. It's not equal to 0 and it is negative. And also, what happens to denominator? As x approaches negative 12 from negative side, x plus 12, the denominator approaches 0, also from negative side. So denominator is negative, the numerator is negative, and we are taking a non-zero negative number and dividing it by a very small negative number. The answer is a large and positive number. So this thing is plus infinity. If our task was just find all the vertical asymptotes, I would stop here. Because now I know that from at least one side my function approaches plus infinity. That's enough to claim for claiming that this is a vertical asymptote. But my actual task is to sketch the graph, sketch the function as well as I can. Yes, I will. But I'm saying that even for vertical asymptotes, I'm not done yet. Because, well, a function might approach plus infinity like this, and even though we know that the function continues to increase, still we might have two different options. Function like this, or a function like this. So we have to distinguish between the two. And the best way is just to compute the upper limit on the right. Okay, but luckily for us, we don't have to think too much about this one. The numerator still approaches a negative number, the same number. The denominator now is small and positive. So the quotient is large and positive, large and negative. The numerator is negative and non-zero. The denominator is small and positive. Okay, so let me also record this result. This small space x equal to minus 12 looks like this. It approaches plus infinity and minus infinity. Okay. So questions about this vertical asymptote?
Could you use your cavity as well to find it?
No, I couldn't, because I still have this option that my function is say concave up, then concave what it should be. At minus 12 concave down, increasing, but still has a finite limit. So I really can't decide in this case. Without computing the limit, the other information doesn't tell me. Yeah?
On the exam, do you have to show vertical asymptotes? Because if you do increasing, I mean, like, if you have to show, like, show the word for this part.
So for this kind of function, yes, you do. If the function is not a quotient of two polynomials, then you actually have to compute all the limits. If the function were a quotient of two polynomials, so something of this kind, but only integer powers of x, then you can just factor out all the terms from the numerator and denominator, and we'll just use the fact that for a quotient of two polynomials, if the function goes to infinity from one side, it will also go to infinity from the other side, or minus infinity. But for this kind of function, no, you can't be sure. Yeah?
Can you compute the limit to x negative from the left-hand side again? Why is that just positive infinity?
This one, so once again, the numerator becomes close to this number, which is negative. The denominator, x plus 12, well, x plus 12 is small and negative.
Yeah.
So we are taking the quotient of its negative number and a small negative number.
But they're
Quotient of two negative. No. So we are taking something like this. Minus 10 divided by minus 0.00001.
Yeah.
Okay? Yes.
You just put it in there.
The other side, you are dividing minus 10 by positive 0.0001. Well, kind of a negative number, negative numerator, something close to this, by a small positive number. So the answer is large negative. Yeah.
I mean, if you know you're going to go towards negative, I mean, to infinity and negative 12, isn't there the only case of judging from the positive cavity and the negative cavity? Isn't it always going to be that?
So I just gave you an example where it is not. Concave up, then concave down, increasing, then increasing, but still has a finite limit. Finite doesn't go to minus infinity, it goes to the finite place. So no. Okay, so let's talk about horizontal asymptotes.
This takes a long time.
So before I talk about horizontal asymptote, let me explain why I start with horizontal asymptote and not with, say, slant asymptote. The reason is because, well, first of all, it's easier to find horizontal asymptote, and second thing, if I do find the horizontal asymptote, I won't have to check for the slant asymptote. My function might have, I have, make a comment here. If a function has kind of two ways, the argument of the function has two ways to go to infinity. To the positive infinity side and to negative infinity. infinity side. At each one of the sides, the behavior of the function might be one of the following. It might have a horizontal asymptote, a slant asymptote, or no asymptote. And the same might happen in the other side. Sorry? Yes, so in each one of the sides, it is an exclusive kind of choice. I have an option of choosing only one of those three. It can't have both simultaneously. It can't have both a horizontal asymptote and a slant asymptote. So a good idea would be to start with checking for horizontal asymptote. If you find one, you know that that's it. And same on the other side. You have only one choice. Okay, so let's talk about this horizontal asymptote. We want to compute what happens to the function when x becomes very large. So I'll take this x plus x to the power 1 over 5 plus 12 over x plus 12. So look at this function. The numerator becomes very large, the denominator becomes very large, the quotient will not clear, but I know what to do. I should factor out the largest power of x. So I rewrite it as limit as x goes to infinity, largest power is just x, 1 plus 1 over x to the power 4 over 5, plus 12 over x, divided by x times 1 plus 12 over x. Now I can cancel out this x. And when x is large, this is small, this is small, this is small. The only important things are 1 and 1. So the quotient is 1. Okay, now we have to, so we find that y is equal to 1 is a horizontal asymptote at this end, when x goes to infinity in this direction. Well, actually, the same computation works when x goes to minus infinity. If okay, so for minus infinity, I can use the same thing, same trick. 1 plus 1 over x to the power 4 over 5 plus 1 over x, 12 over x, over 1 plus 12 over x. When x is large, even though it's negative, still this is small, this is small, and this is small. So the quotient is still 1. So y is equal to 1 is a horizontal asymptote at infinity and at minus infinity. Okay, so basically we are done with all the computations, more or less. Now we are ready to start actually sketching the graph. So it's not a polynomial. This thing, x to the power 1 over 5, is 1 over 5 is not integer, so it's root of something. Yeah.
How do you differentiate between horizontal asymptotes and slant asymptotes?
So if at this step I try to compute this horizontal asymptote and I got say infinity, then I know there is no horizontal asymptote. Next attempt, try for slant asymptote. For slant asymptote, I'll compute this A and B using the two limits. If they fail, then you have just no asymptote. Yeah.
The slant asymptote, by the definition, you already know if the denominator is 1 power lower than the numerator. we should check, right?
That only works for a quotient of two polynomials.
Yeah,
This is not a polynomial.
Oh,
This fifth root of x
Yeah.
is not a polynomial.
only polynomial works.
Yes. Other questions?
It's when it's like x squared, x plus x cubed. As long as it doesn't have the fractions of all.
Oh, yes. So if instead you were you were to try to do it in the reverse order, first find the slant asymptote and then if it fails to find the horizontal asymptote. Let's look what will happen. So
It's the best way.
really good question. So well, kind of smart, but if we start with slant asymptote. So the question was, suppose we were that smart and we didn't start with horizontal asymptote. Suppose we were to start with a slant asymptote. What would we do then? Well, it's a natural question. I mean, will it work or will it not work? And the answer is, in fact, it will work. Let's try. A, we'll have to find something of this form. Y is ax plus b. A must be the limit as x goes to infinity of f of x over x. Then we'll find it like this. It's the limit of x plus x to the power 1 over 5 plus 12 divided by x and by x plus 12. Well, what is this limit? Let's factor out the largest powers and see. Its limit as x goes to infinity of 1 plus x times 1 plus 1 over x to the power 5 plus 12 over x and x squared 1 plus 12 over x. So this limit is actually 0 because this part approaches 1 and this 1 over x approaches 0. And now we are back to the same game. Now we know that the slant asymptote, whatever it is, will have a equal to 0. So it will in fact be horizontal. So the asymptote is horizontal. So you see, the method still works. It still produces the correct answer. The only problem is you make one extra step. So now you'll still have to compute this b, and it's still computing the same limit.
So if it's a slant asymptote, you get a constant for a.
Yes, if I get a non-zero answer, it is a slant asymptote. That's really good question. Okay, so let's go to actually graphing. Okay, we have several points here. They import minus 12, 0, 3, minus 20. So minus 12, 0, minus 2, 3, and 8. X equal to minus 12 is a vertical asymptote. Y equal to 1 is a horizontal asymptote. My function is increasing the concave up all the way up to minus 12. And I know that it is, well, it must approach plus infinity here, and it must approach the horizontal asymptote here. So it has basically no choice but doing something like this. Okay, I also know that here it approaches minus infinity. Next I know at point minus 2 my function changes concavity. It's concave down, then it will become concave up. And all this is while my function is still increasing. So it increases all the way up to 0. Okay, so my function will be increasing, changing concavity, and then increasing once again. I naturally have lots of ways of drawing it. I can draw it like this, or even higher. It would be interesting, to distinguish between all those ways of drawing. The natural idea is to find what is this point when x is minus 2, what is f of x. So let me erase these wrong pictures and make some computation. Oh. What is f of minus 2? Well, it's minus 2 plus negative 2 to the power 1 over 5 plus 12 over minus 2 plus 12. So it is 10 minus 2 to the power 1 over 5 over 10. So what is it? Well, it's 2 to the power 1 over 5 is something really close to 1. So this number is pretty close to 1 but slightly smaller. So it is almost on this line but a little bit below it. So put a point somewhere here. And now go all the way up to this point and change concavity here. My function is still increasing at this point, so I don't try to make it horizontal tangency here, it's just, well, increasing. Next interesting thing happens at x equal to 0. I will have a vertical tangency. My function is concave up and has vertical tangency at 0. And once again, several options. I can make it like this, or even higher. Once again, just this process forces me to try to compute f of 0. So I do. F of 0 is 0 plus 0 plus 12 over 0 plus 12. So it is 1. So in fact, my vertical tangency happens exactly at this point. So I erase these things, and my vertical tangency is here. Then the function changes concavity and has a maximum at the point 3. So something like this. Once again, it's a good idea to know how far it goes all the way up to maximum. Is it really high or is it close to this point 1? So we'll compute f of 3 as well. So 15 plus 3 to the power 1 over 5 over 15. Fifth root of 3 is still quite close to 1. It's a number whose fifth power is 3. 1 to the power 5 is 1, but 2 to the power 5 is already 32. So 3 to the power 1 over 5 is pretty close to 1. So this thing is close to 1 plus 1 over 15. It's just a tiny bit above 1. So maybe this was an exaggeration actually. It should have been much closer. Okay, so here I will have a local maximum, and my function will start decreasing. Then it will start decreasing, and then it will change concavity at the point A. Okay, maybe once again, a good idea is to understand what is the value of the function at this point A. So it's 20 plus 8 to the power 1 over 5 over 20. Still, fifth root of 8 is, well, maybe 1.3, 1.4, something like this, but not not really huge. So it's still just a little bit above this line. But of course below this point, because my function is now decreasing. So I draw something which is concave down this segment, and then it is concave up, and must approach this line. Okay, so let me summarize. My function is so my function is increasing and concave up, goes to infinity, returns from minus infinity, is concave down and increasing, still concave down and increasing, then concave up but still increasing, has vertical tangency, concave down and increasing, concave down and decreasing, concave up, decreasing, and approaches 1. So all the features that we wanted are now represented in this graph. Okay, so maybe now any questions about the graph? So maybe as an answer to your question, well, you see, we actually had to compute the values of f, the y values here, because otherwise our graph would be all over the place. We wouldn't actually have any answers here. Okay, so other question? Yeah.
But we don't really care about the accuracy of the
of the roots? So how this? So well, I mean, on the midterm, I believe that one of the questions for graphing will be find the x and y intercepts. For this, you'll have to solve f of x is equal to 0. F of 0 is something. But here, I mean, it will be pretty easy on the midterm. So don't worry about it. Just for this function, if you were to try to find the x-intercept, it would be quite impossible. So I was answering the question of whether you should find x-intercept, and my answer was on the midterm it will be probably one of the questions, and so you will be explicitly asked to find the x and y intercepts. But for our question, first of all, it doesn't seem that important, and the second thing, it's quite hard to actually find this example. Okay, other questions? Sorry? No, no calculator. Okay, so let's okay, let's switch to another topic. Let's switch to another topic, it's optimization problems.
No, they said they'll give it up to 3. They said.
Okay, let's try this problem. We'll start with an example, but it is a very typical example. The ball is placed in a cylindrical mass. of radius 20 centimeters, 10 centimeters. For what radius of the ball? Is the most water is required to cover it. To cover it completely. Okay, so as you see from this problem, let me read it. The ball is placed in a cylindrical mug of some radius, and the question is for what radius of this ball the amount of water that is required to cover it is the largest. So as you see, an optimization problem is basically a problem to describe some situation, in this case a ball in a mug, and in this situation you are free to choose some parameters, in this case the size of the ball. And what you are trying to achieve is to maximize or to optimize some quantity. So for some reason, in this case, you want the most water to be necessary to actually cover this ball completely. It might be, well, optimization problems appear in different contexts. Maybe you want to optimize some manufacturing and you have as your variables, well, the schedules of your workers. Maybe you want to optimize the business profitability and, well, your variable might be the price or quantity produced, of course. So in all these situations, basically you have some variables which are changing parameters. They are changing, in this case, the radius. And you also have some target function. In this case, the volume of this water. And the question is for what values of the parameter, the value of the target function, the volume is, in this case, the largest, or might be the smallest. So how to approach these questions? Well, first idea is to understand really well what the question is asking. Because if you start to solve a question but it's the wrong question, well, you'd better not even start. So here we have a cylinder, and inside of it we place a ball. Then we try to pour inside of it some water in such a way that it covers this ball completely. And the question is, well, now you measure how much water is inside of the cylinder, and for what radius of this ball the amount of water is the largest. So a parameter here will be the radius. And target function will be volume. And we want to maximize volume, find the value of R which maximizes the volume. Next part is, well, let's try to write our function as a function of these parameters. So what is the volume as a function of this radius? So any ideas how to find it? Say it again? Pi r squared times what? Oh, okay. So indeed, if you pour inside of this water, you'll have the water fill a cylinder like this. The volume of this cylinder is pi times the radius of the base, which is 10. So 10 squared times the height here. What is the height?
Diameter of the ball.
It's the diameter of this ball, which is 2 times r. So this is 2R. Okay, but that's the volume of the cylinder. That's not the volume of the water. What is the volume of the water? Well, the water fills the whole cylinder except the ball itself. So we should subtract the volume of the ball, which is quite easy. It's just 1/3 pi r cubed. Okay, so now we have an expression for the target function volume as a function of the parameters. In this case, we have just one parameter. Yes, that's the volume of ball. It is 4/3, yes. Sorry. You're completely right.
You're so funny.
Okay, so now we have the correct expression for the target function. And before we try to optimize it, we should write down some constraints. I mean, not every value of R that we might find or might suggest will actually work. What do I mean? What if I try to optimize my function and I get that the optimal R is negative? Then something is definitely wrong. So we should have some constraints. The radius is definitely positive. But that's not enough. What other constraint is important? Yes, so it must be smaller than 10. The ball must fit inside of this cylinder. Otherwise, well, it won't make sense. Okay, that's it. If we get any answer in these bounds from 0 to 10, we will get a ball of positive radius which will fit inside the cylinder.
Isn't it 5 because twice the radius is your
So 10 is the radius of the cylinder, and 10 is also the radius of the ball. So it's 10. Okay, so now we have a completely mathematical problem. Find the maximum of this function on this interval. And now we know how to approach it. So find maximum of V of R between 10 and 0. Completely mathematical problem. We find derivative with respect to R, which is, well, I have 200 pi minus 4 pi R squared critical points. So critical points happen when this thing is equal to 0. I mean, it could happen that critical point is where derivative is 0 or doesn't exist, but in this case it will always exist. So it's only v prime of R is equal to 0 or 200 pi minus 4 pi R squared is 0. So R squared is 50. So 500, not 550. 50. So R is R is plus or minus square root of 50. Okay, so next part I have to do two things. One is remove all the things, all the points which do not satisfy my constraints. So even if one of these points is maximum, say minus square root of 50 is maximum, it's not good for me. Because well, it should be positive, the radius must be positive. So r, which is minus square root of 50, doesn't satisfy this constraint. We also have to check for the other one. R equal to square root of 50. Well, it does satisfy both constraints. It is smaller than 10 and bigger than 0. Square root of 50 is about the same square root of 49, which is 7. So it is really smaller than 10. But it's still not enough, because, well, you know, you might have a critical point which is not the local maximum at all. We are quite familiar with this situation. Something like this. This point would be a local a critical point which is not a local maximum. So we have two ways to approach this. Either we notice that my function is a continuous function and then on a closed interval, and then it must have a maximum, and then we'll just compute. So let me give you both approaches. Approach 1. So I want to find the actual maximum. So finding the actual maximum. One way is just notice that my function is continuous, and then I'll compute b at the endpoints, and also b at this square root of 50, and then compare those. So b of 0 happens to be 0, b of 10 is complicated. So 5 times 1000 minus 4/3 times 1000. So it's here it was 2000. So it is, that's what it is, and here you also compute and you'll compare the values. So sorry, I won't finish this computation because I want to show the other way also. The other way would be directly check that this point is at least a local maximum to exclude this kind of situation, to exclude that it's actually a minimum. How do we do this? Well, compute the second derivative. Second derivative is, in this case, minus 8 pi r. So the second derivative at the point square root of 50 is definitely negative. Minus 8 pi times square root of 50. So my point square root of 50 is in fact a local maximum. But then it's the only local maximum on this interval. My function must increase all the way from 0 to this point, and then decrease from this point all the way to 10. So it must be also, so it's the only local maximum, hence it is absolute maximum. So now I have a complete justification. This point square, this radius square root of 50 is the optimal solution. For it, this folding will be the largest. Okay, so good luck today and see you next time.